And what I'm going to do is that I'm going to start the introduction, so I will we'll start again at 1 o'clock, so because the topic is quite broad. My goal is to explain you how to solve the optimization problem. So last week we have seen that we can state the optimization problem in different ways. That the optimization problem was always appearing from the numerical point of view as an objective function to be minimized or maximized. And we are going to minimize or maximize this objective function in the context of a list of constraints that are representing the models that we have. The constraints are expressed in equality and inequality constraints. And the equality constraints are going to define the number of degrees of freedom of the system. The number of degrees of freedom being the difference between the number of variables for which we would like to know the value and the number of equations that can be used in order to fix the value of the variables that we would like to know. Okay? And if the number of degrees of freedom is bigger than 0, the problem cannot be solved because we still have degrees of freedom. And we are going to fix those degrees of freedom by having an objective, which is, for example, minimizing the cost, the total cost of the system. That's what you have presented this morning. Okay? So it means that we have to find, and what I'm going to discuss today is the solving methods that can be used in order to solve the problem of fixing the value of all the values that are not bounded by equations, fixing the values of all those variables in such a way that they will minimize an objective function. Okay? So the goal of the optimization is really to fix the values of the degrees of freedom with a given purpose, which is the objective function that needs to be optimized. So what I'm going to do is that I'm going to discuss a little bit first the type of problems that we can have. So the 1 degree of freedom first. Then I'm going also to discuss the type of problems that we can have to finally make a very short introduction, a very short introduction of the mathematical methods that can be used in order to solve the optimization problem. So typically in mathematics, I would say that what I'm going to present in maximum 2 hours of lectures is typically something that the mathematician will get 3 to 5 to 6 credits. Okay, so I have to go very fast. And therefore, I'm not going to go into the details of the methods. I'm going to show you what are the consequences for you. So when you will activate those numerical methods. So the first thing we have to look at is what is the definition of an optimum. And typically, an optimum is the place where either we reach the maximum point for a concave function or a minimum one when we have a convex function. And we know from your lecture on analysis that the maximum is defined by the place where the derivative of the function is equal to 0. Okay? Reaching the maximum when the derivative is equal to 0, which is what is shown here in this by this relationship here. Okay? In reality, it's a little bit more. It's not only sufficient. It's not sufficient to have a derivative equal to 0. In reality, you have to have a derivative equal to 0, and you have to be sure that you are climbing in both directions here if you are looking for a maximum, or decreasing in both directions around the minimum when you are looking for a minimum, which can be translated by this equation here. Okay, so it means that if you move apart in both directions, and if you are looking for a minimum, then the function will, in both cases, increase from the position of the minimum. Okay, And that can be then translated when I'm in the multiple dimensions by the fact that the matrix of the second derivative needs to be defined positive. Okay? Which are all notions that you have learned when you were in following the lectures on in analysis. So in reality, when I'm saying this, it means that if I'm looking at a very complex function like this one, okay, there are different cases in reality. So there are points where I have a local minimum. So for example, here I have local minimum. Here I have a local maximum. I can also have points where I have a derivative that is equal to 0, but the second derivative conditions is not satisfied, which is an inflection point. Okay? And if I'm now looking at the whole search space, there will be a global maximum, which is the maximum of the maximum, and a global minimum, that is the minimum of all the minimums that I have identified. Okay? And this then can show the difficulty from the mathematical point of view, because if you have a very big search space, and if you are looking for the minimum, then you are trying to find this point. Okay? And the problem is that you will also see this one and this one, which satisfies the conditions. Okay? By chance, and this was already highlighted a lot in our in the previous lectures, the search space in X, when we are solving engineering problem, the search space is always bounded by the significant or the consistency of the model that is going to limit the validity of your model to some extent. Okay, so I'm not going to look at the square centimeter PV panels. I'm looking for square meters. Okay, so it means that I know that I have to look in the square meter scale, and most probably then I have a higher chance of having only one optimum. Okay, this is for the objective function. The second dimension is the fact that I have constraints. Okay, which are the models. So I do not have only a simple search in an unconstrained domain, but I'm constrained by the models, which means that there are relationships between variables. And those are represented on the one hand by the inequality of the decision variables, but also by the fact that there are relationships that are created by equality constraints. So the mass and energy balances are written here, and inequality constraints, that is, for example, telling me that the flow, that the sum of the flows needs to be bigger than a certain value. Okay, this is what we write. You have written in the set of equations that you have added. Okay, so this is the constraints, so objective function constraints. And now if I'm looking at the collection of different types of problems that I can have, what we can see is that both the objective function and the constraints can be linear or non-linear. Okay? So linear means that the equations can be written with a matrix that multiplies the variable plus another term that will be expressed as being the right-hand side of the equation. Or nonlinear, meaning that in this case there is a function here, which is a function of the variables and some parameters, but that has nonlinear relationships. Okay, so it means that at the end we will have different types of optimization problems. When the objective function and the constraints are linear, then we will be in the field of the linear programming domain. Now we have to realize as well that the variables can be either continuous, so it means that they can take any value between the minimum and the maximum bounds, or they can be integer, meaning that they can take only integer values, 0, 1, 2, 3, 4. Okay? If you have only continuous variables, then the problem, and if the constraints are linear and the objective functions are linear, then you will have a linear programming problem. If you have only integer variables to consider, then you will have what we name an integer linear programming problem, which is has exactly the same form here. So all the equations are linear, the objective functions and the constraints, but the values that we are looking for are only the integer. So the example is, how many trucks do I need to transport a certain amount of goods from one place to another? It's 1, 2, 3, and not 2.5. Okay, a 2.5 truck doesn't exist, right? So this is an integer linear programming problem. And then sometimes we will have a mixed integer linear programming problem. This is exactly what you have solved already. So it's a problem in which there are some values that are continuous, at which level do I use the unit, and integers, which one of the unit do I use, 0 or 1? Okay? In this case, it's a mixed integer programming problem, and if all the objective functions and the equations are linear, then it's a mixed integer linear programming problem. Now, if some of the constraints or some of the objective function is nonlinear, it can be quadratic or even more complex, then the problem is becoming a nonlinear programming problem. And if you have integer variables, then it can be mixed integer nonlinear programming problems or integer nonlinear programming problems. So those are all the terms that are needed. And for each of those type of problems, there will be specific methods to solve it. Okay? And let's start with the first step, linear programming problem. And when I'm defining the objective function of a linear programming problem in a 2D, so I have just the objective here, and I have just one variable here. So I have a problem with the definition of the minimum, because there is no minimum in these objective functions. The objective function is going down. Okay? So where is the minimum? The minimum will be defined by introducing constraints. So the inequality constraints, that is going to be represented by a straight line here, the min and max bounds, that is going to define the search space in which I'm looking for the minimum. Okay? And in this case, only, so if I have the inequality constraints, then I will be able to find the optimum. Okay? And there is no curvature, there is no place where the derivative is equal to 0. Okay, because the derivative is a constant. Okay? So what does it mean? It means that if you are solving linear programming problems, the goal of the solver will be to identify which one of all the inequality constraints that you have here, which one, so being on the variables or in the combinations of the variables, which are linear combinations, which one has to be transformed from an inequality to an equality constraint. Okay? Of course, I could have had other inequality here. And in this case, for example, when I have obtained this optimum here, the value of the variable is not at its minimum bounds. Huh? Okay? So what does it mean? It means that the solving methods that are going to try to solve linear problems will always try to identify and will look for the identification of which one of the inequality constraints has to be transformed into an equality constraint. And that's the way the methods for linear programming are working. Okay? So, and this highlights the importance of bounds when you solve a linear programming problem. Okay? Now, this is the first type of problem. This is the one that you have solved, and in reality you have solved a mixed integer linear programming problem, not linear programming only. What does it mean? It means that some of your variables that you had here, that were between 0 and 1, needs to choose between being equal to 0 or being equal to 1. Okay? So in this case, in fact, I have to some extent two problems. Do I have to choose between 0 or 1? Okay? Compared to this problem where I have only to choose what is the value between 0 and 1. And what I have seen here is that the value can be in between. Okay? So how is the system, and in addition to this, so I do it for one variable that is an integer variable that needs to be either 0 or 1, but in reality, I have to do it with the combinations of all the integer variables that I have in my system. To some extent, I have to test if I'm buying the heat pump, if I'm buying the boiler, if I'm not buying the heat pump and the boiler, or if I'm buying the two. Okay? And then if I'm doing it with fuel cells, heat pumps, cogeneration units, PV panels, etc., I will have to make all the combinations of all the possible combinations. Okay? Now the way we are going to solve the problem, in order not to solve a very big list of new problems, okay, there is a trick, and the trick is the following. So the first thing we will do is that we are going to fix to consider that all the integer variables will be between 0 and 1. Okay? And then I know that I have to explore all the possibilities by adding a constraint. And the constraint is going to say, now the value, instead of being 0, instead of being between 0 and 1, is going to be 0, and then another option is going to be 1. Okay? And what I'm going to do is that I'm going to add this equation. So I'm adding the equation z is equal to zi is equal to 1, and another equation that is going to say z is equal to 0. When I'm doing this, I'm adding a constraint to the system. Okay? I'm fixing the value. And by definition, either the objective function of the original problem will be the same. It means that in fact the value was at the bound already, or will be worse, because I'm adding a constraint. It means that it was not the optimum, so it means that it is worse. Okay? So it means that now, each time I'm going to solve the problem, I'm going to add constraints that is fixing the value to 0 or 1, all the others being still continuous. Okay? So it means that now, if I'm adding systematically constraints that fix the value to 0 or 1, I'm going to create a branch, which is a collection of new constraints that are added, and each time I'm adding constraints, the objective function is going to be worst. Okay? If I'm doing it in this way, at a certain time I will have the complete set of integer variables that are either 0 or 1, following one branch. Okay? And this value, the value that I will obtain from the objective function, will be the worst one that I will accept until now. Okay? And afterwards, what I'm going to do is that I'm going to go back to my branch here, and I'm going to say, okay, well, here I have set to 1, but I should have set to 0. So I'm going to explore this branch. Okay? So it means that I'm restarting the problem. So now I have obtained this solution, for example. I'm going to go back, and I'm going to observe what is going to happen by switching from this solution to this one. And I have to do it in a systematic way, because I have to explore the whole set of possibilities. So each time I have added a constraint to 1, I know that I have to add, I have a complementary problem that is the constraint set to 0. Okay? But something which is important now is that I'm doing it with, so if I'm here, I know that the remaining one are still continuous, so I do not need to fix the value to 0 or 1. But when I will be here, I will test the value of the objective function. And if the value of the objective function of this branch here is going to be low, I'm looking for a minimum, so it's going to be higher than the one where I have the full complete sets of constraints equal to 1, as I know that if I continue to add constraints, it will be worse, okay? Then I know that I can stop. I do not have to explore the rest. right? And by doing this, and this is what we name the bounding strategy, it allows me to be very efficient and does not force me to explore all the branches, okay? Because I will have to explore only the branches that have a certain chances to still increase my worst case. And as soon as I have another set of integer, a complete set of constraints that fix all the values of the integer variables, so that I'm sure that I have only integer variables in the solution, if the objective function is better, so the minimum is better, then it is going to become the next worst solution that I will accept. And when I will have finished to explore the whole space, then I will decide this is the optimum solution. Okay? So this is what we name the branch and bound strategy, which is, on the one hand, generating in a systematic way with the branching system a collection of new processes, of new problems that are created from the previous one to which I'm adding one constraint, okay? With a bounding strategy that is going to tell me that as soon as I'm reaching the value of the worst case, I do not have to finish to explore the whole combination of integer variables. Okay, so this is the branch and bound strategy. Okay, that's what is going to increase the speed of the solving procedure. And if you are using professional tools like the one that you are using in the exercise, in fact, what we can see is that if you have a very nice strategy to find from the beginning the best solution or the most probable good set of integer solution, then we will have the possibility of eliminating a lot of other explorations because the bounds will be good. Okay, and the tools that you are going to use have a lot of heuristic rules, so it means that it's not it's just something which is coming from the experience of the programmers that says, oh, if we have this, then it's better to try this integer variable first, so they look at the shadow prices or the derivatives of the subproblems in order to try to be smart in identifying as fast as possible an integer, a full integer variable set in such a way that the branching, the remaining branches to explore will be very small. Okay, just for you to know that this is why you can always write the algorithm from a book, but if you buy an algorithm, a solver on the market, it will be much more efficient than the one that you can program yourself. Okay. And that's what indeed defines as well the value of buying a software rather than writing all the equations by yourself. Okay? So now let's discuss the second dimension, which is the dimension of the nonlinear programming. In nonlinear programming, it means that I do not have, I'm not sure that the optimum will be on a bound, because it can be where there is a curvature and there will be a place where there is a minimum. In this case, the problem becomes a little bit more complicated to solve, and we will use, like what we were doing in solving equations, we will use iterative procedures. There are three types of iterative procedures. The first one is what we name the direct search, is that we are going to explore the space of the solutions in a directed way, I would say, in the sense that I'm going to make a step, look where I am, and look if there is a decrease in the objective function, if I'm looking at the minimum. If there is a decrease, then I will do another step from the place where I am, and I'm going to progress until the time where I have identified where is the minimum. So let's assume that I am in this room. I have constraints which are defined by the walls. Let's assume that now the roof, it's not the roof. How do we say? The floor, yeah, the floor. Let's assume that the floor is has a curvature, and you have to reach the minimum. Okay. And let's assume that you are blinded, so it means that you do not see where is the minimum because you do not have time to calculate all the points here. So what you will do is that you are blinded, and then you will progress and then see if you're going down. If not, then you will go back, and at the end you will be able to identify where is the lowest point in the room. Okay, perhaps it will be on the walls. Huh? So this is the direct search method. So we do it in a systematic way, step by step, until we find where the minimum point is. The indirect search method is going to say that, okay, I know the definition of the optimum. The optimum is the place where the derivative is equal to 0. So in the indirect search method, what I'm going to search for is where the derivative is equal to 0. So it means that I'm not looking for a descent, I'm looking where the derivative is equal to 0. Okay? So this is the indirect search method. And then, but I will not discuss this today, the heuristic methods are the third type of method that can be used in order to solve an optimization problem. And in this case is if you have computing power available, because then you will explore the space by sending soldiers everywhere. And each soldier is going to come back and give you the information about what is the height. And then you will say, okay, it seems that it is in this direction. Then you send new soldiers there. And each one is going to come back with the new value of the height. And you will finally decide which one of the soldiers is the one that has identified the minimum. Okay? But each time I'm sending a soldier, I have to make a calculation about the height. So if I have 3,000 soldiers, it means that I have to calculate 3,000 times the objective function. If I'm doing steps, I have to calculate the objective functions only at the time where I'm making the step, 3, 4, 5 times. Okay? So it means that this one is going to explore, it will cost much more, but this system will be able to identify the global optimum. If I'm starting from here and there is a trap here that is a local minimum, I will be trapped because I will have no information about the possibility of having another place where it is lower. Okay? So it means that those methods are quite nice when you have to be sure about the places where you can find the optimum. Okay, now let's look at the direct search methods before the lunchtime. So the direct search methods are methods that are exploring, and I'm going to look at first a system where the only constraints that I will see is the constraints on the decision variables. So let's assume that I have first a one dimension. So let's try to find this point here, which is the minimum. Okay, I have x here and the objective function that is here. So what I'm going to do is that I'm going to try to identify where this point here is by constraining my search. So what I'm going to do is that I'm going to make steps, and as soon as I see that I'm decreasing the objective function, then I'm going to continue to progress. And as soon as I see that the objective function is going to increase again, then I know that the optimum is, if my objective function is increasing, I know that it is in between the 2 points that I have made. Okay? And then I'm going to try to frame the position of the minimum. So I will go from here, step by step, then I see that it is going to increase. So now, I'm going from here, I'm going here, I'm going here. Oops, it is increasing, so I know that it is between this point and this point. And I'm going to choose something which is in between, so that at the end, between this point and this point, and then I'm going to, between this point and this one, I'm going to decrease the search space, and finally I will concentrate on where the minimum is. Now, how do I choose what is the next new point? there is a trick which is a gold number, and the gold number has allows me to calculate where to find to define the new x, okay, by defining in fact modification of the interval that is such that I will never reproduce a step that I have done before. So I'm sure that I will not be stuck by doing something which is oscillating because I'm dividing the step size in a systematic way. So this is the principle of the gold number. This is one way of doing it. Another way is to be really smart. So you remember from your lecture in analysis, and you know that if you have a function with 3 points, so if you have 3 points, you can always approximate the function by a quadratic curve, okay, which has this form here. Okay, so you have 3 unknowns: the A, the B, and the C. And if you have 3 points, you can calculate A, B, and C in an analytic way, with the 3 value of F1, of 3 value of F. Okay? And then what you can say is that, okay, if the function is quadratic, I know that the minimum has to be where the derivative is equal to 0. And as I can solve this problem, I will be able to analytically calculate where the x, the best value, is going to be located. Okay, and then I will calculate the new value here, and I give you the analytical formula that allows to do it. Having the new value, then I will eliminate the one that has the highest objective value of the objective functions, and I will redo the job here. Recalculate the A, B, and C, and calculate the new value of x star. And then, of course, I will have to decide the termination criteria, which is exactly the same as the one that I was using in all the iterative procedures that I had before. Okay? So this works for one dimension. Now, if I have more than one dimension, then I will have to be smart. The way to be smart, if my goal is to find the value of an objective function, is to learn from the past. So it means that I'm going to try to identify in which direction I have to search, and the direction is going to be obtained by looking at what is the slope giving me as an information of the direction of the slope. And I will have also to decide, because the slope is going just to tell me that I'm descending, but I do not know how far I have to go. So it means that I will have also to decide what is the step size that I need to realize. Okay, and this will allow me to calculate the new point in the iteration. Now, for choosing the step size, I can either make a fixed step that I fix a priori, or I can solve a 1D optimization that I had just before. Okay, so I'm making then 3 steps in the direction, and then I can approximate it with a quadratic function, and then make an iteration to define what is the best size of the step. Okay? So what we can see here is that the new point depends on the previous one. Okay? So now we have the same constraints as the same requirement as when we were solving nonlinear problems. The better the initial guess is, the highest chances we have in finding the optimum. Because if the first guess is good, then the slope is already a very good indicator of where, if it is descending or not. Okay? And of course, if it is not descending at all, the step will be 0, and I have the optimum. Okay? So it's exactly the same principle. The better the initial point is, the better will be, or the faster will be the solution. In addition, I can also be smart in learning from the past. And so what I can do is to generate the value of the step of the k plus 2 using the value of the k plus 1 and the value of the k that I had before. So it means that now I'm not only looking at the slope, but I'm also looking at the curvature because I have 3 points, okay, in the multiple dimension. And in this case, that's the technique of the conjugated gradient, is that I will be able to approximate the shape of the search space in such a way that I will go faster towards finding the optimum. Okay? So still in the unconstrained, and this will be my last slide before the break, still in the indirect, unconstrained problems, the indirect method is going to look at the expression of the conditions of optimality. So what does it mean? It means that if I have to solve this problem of f of x equal to find the minimum of f of x, or define the value of x in such a way that the f is minimum, I can always define this as being the equivalent to find what is the value of x that makes the derivative equal to 0. Okay? And in a multi-dimensional domain, what does it mean? It means that I'm going to search for a set of equations in which the derivative of f is equal to 0. So I'm transforming an optimization problem, which is in one dimension, so I have only the objective function. I'm transforming it into an n-dimensional problem, n being the number of degrees of freedom, okay? Which is a set of nonlinear equations that needs to be set to 0. So this is now the gradient of the objective function that needs to be equal to 0, and I have n equations, n being the number of degrees of freedom. Okay? And as soon as I have written this, then I know how to solve a problem with a set of nonlinear equations. So you have learned how to do it. Initial guess, Newton-Raphson method to find the next step of the set of decision variables until the time we reach the conditions of convergence will be defined by this value, all the derivative being equal to 0. Of course, there is a consequence to it, is that if I have to do this, I need to, in fact, calculate the derivative of the derivatives if I want to do the gradient. Okay? Which means that I will have to have an approximation. I will need to calculate the derivative of the derivative, which is time-consuming, because I will have to make perturbations on the derivative of the objective function. Okay? So it's time-consuming, but it allows me to find the value of the optimum. Okay, and as I am smart, I can also declare that the objective function that I need to minimize can be approximated using the Newton-Raphson, using the Taylor development that can be then limited, that will be limited to the second degree, so not the first order but the second order. Now I have an approximation of the objective function that has, in fact, here the second derivative, so the Hessian matrix is the second derivative, and I can express the conditions of optimality as being the gradient of this Q being equal to 0, which allows me then to calculate what is the step to be done for the decision variables in such a way that the conditions of optimality, that is delta Q equals 0, will be satisfied, which will allow me to calculate what is the best value of the value of the decision variables. Okay, so second order of the Taylor development, and then which is similar to apply the Newton-Raphson method. Meaning also that we have to learn from the past what we have learned for the solving procedures. So if the system is going to be will have problems to if the gradient here will be not decreasing, so the value is not decreasing here, so the norm is not decreasing, then it means that we have to apply the relaxation method because the slope is not giving us the right direction. Okay, it's not approximating well the objective function, and in this case you will have to be to apply the relaxation, which allow you to then make smaller steps, but with the guarantee of going down to the optimum, which to some extent means that with smaller steps you will follow the steepest descent, so you just take the information of the descent, while if the function is not far from being a quadratic function, then you will make the full step of the Newton method. Okay? So, conclusion of this first part, if you have to minimize an objective function which is nonlinear in a multi-dimensional domain, you have two choices: a direct search, exploration only, or an indirect search, looking at where the minimum is located by defining the conditions of optimality. Most of those techniques need a very good initial point, okay? And the techniques that apply, that are in the indirect search approach, the techniques needs the calculation of the second derivative. So it means that I will have to make the derivative, and for the derivative I will have to make another perturbation to find what is the second derivative of the function, which is time-consuming in terms of calculation. Okay? And you enter into the iterative process, meaning that you will have to apply the criteria of convergence on the variations of the variables and on the distance towards the zero of the derivatives. Okay? If you use an indirect search method. Do you have questions about this? If not, then I will start again at 1 o'clock, 1:15, okay? With the other part where we are going to add the constraints to the problem. So this morning we have seen the methods to solve problems when we have to minimize an objective function that was nonlinear one with more than one variable. So there were mainly two major strategies, which was the direct and the indirect search. So this afternoon we are going to try to solve the problem where, in addition to minimize an objective function, we have to deal with constraints. Constraints that can be in a form of equality constraints or inequality constraints, which is lower than zero. And this kind of approaches will be well suited when you formulate the problem as a simultaneous problem, so where you do not really decide which are the decisions variables, but you look at the whole set of variables at the same time, or in the two-level approaches in which perhaps that there will be some of the constraints that will be solved in an internal procedure, but you will have to find the value of the decision variables in such a way that at the same time they minimize the objective function and they satisfy constraints which are nonlinear, so a set of equality and a set of inequality constraints. In addition to this, then you have obviously always the constraints that apply, which are linear constraints that apply to the decision variable considered. Okay, how do we solve this problem? So what we can see is that the first difficulty that we will have is the nonlinear equations involved in inequalities. And in order to help in solving this problem, there is a trick that can be used, is to add one new variable, so which will be a new decision variable, S, which is named the slack variable. And a slack variable is going to measure the distance towards the inequality constraint. And it's going to measure the distance, and by doing this, then what we do is that we introduce a new constraint, which is then an equality constraint now. It is going to say that the constraints minus the slack variable is equal to 0. And what you can see, if you take the square of the slack variable, you are sure that this equation here will always be satisfied. Okay? So now, instead of having an inequality constraint, I have added an equality constraint, and the slack variable that is added to the system is going to represent the inequality constraint. Okay? So I have added a new equality constraint, which is nonlinear, and I will show you why it is important to consider this square in the analysis. But by doing this, then we will be able, we have now only a set of nonlinear equalities in the analysis. And I have only inequalities that are expressed with that are linear inequalities applying on the variables. So now I have a new problem that I have to solve, and I have to find ways to solve this problem. And there are two different approaches that can be applied. The first approach is to say, okay, we know that we have a set of constraints that is here, okay, meaning that there is a set of values that can be calculated as soon as I'm solving this set of equations. So it means that if I'm looking at the number of equations that I have here, the number of variables for which I would like to know the value which is here, I can deduce from this amount the amount of equations that I have here, meaning that now I can divide the set of decision variables into two subsets. On the one hand, the one that we will name the non-basic variables. And on the other one, the set of basic variables, and the set of basic variables are such that if I'm fixing the value of the non-basic variable, I will be able to calculate the value of all the others by solving the equations of the model. So it means that I'm fixing the value of the non-basic variable to a certain value, and by doing this, I have a square problem that allows me to calculate the value of all the, what we name the basic variables. Okay? Which means that now I will have a new function here, which will be, which will tell me that the value of the basic variables is a function of the value of the non-basic variables. And this function is such that I'm solving the set of equality constraints that I have. Okay? So it means that now each function, each basic variable is becoming a function of the non-basic variable, which means that now I can formulate a new problem which has no constraints anymore, okay? Which depends only on the non-basic variable, because each time I'm fixing the value of the non-basic variable, I'm able to calculate all the other one by solving the set of equality equations that I have in my system. And now I have an unconstrained problem, which is find the value of the non-basic variable in such a way that the objective function, which is a function of the non-basic variable, and the basic variable that are calculated as a function of the non-basic variable, is minimum. Okay, and in this case, I have the inequality constraints that applies here. But there is something which is important here, is that unfortunately, the basic variables have also a validity range. And therefore, the equations that are here are, in fact, nonlinear. The same for the slack variables that are in a function of the non-basic variables. So there is a risk that I will not be able to solve the problem with the nonlinear inequality constraints. But the advantage of having this is that I have reduced the size of the problem, because I have eliminated a lot of variables that I have to some extent associated. Each equation, each variable is to some extent associated to one equation. Okay, so it means that I have a much smaller problem to be solved. And then having this, then I can go back to my techniques, to the techniques that I have, in order to solve a non-constraint problem in a nonlinear domain. Okay, and of course, this will be the difficulty here, which I will introduce in my strategies by limiting the steps that I will do. So if the step is going to drive me outside the feasibility zone, then I will have to go back. But okay, what is important is that the size of the problem has been reduced. So if you, this technique is known as being the reduced gradient method. And if you have already once solved an optimization problem in Excel, who has already tried to solve a problem in Excel? There are some functions. The Excel system is using this approach, so the generalized reduced gradient method. Okay, so it means that they identify in the list of the cells that can be modified the one that are the major one, and you in fact give the indication about which are the major one. They solve all the other cells that are a function of the major one, okay? And then they apply this method here to solve the problem. It's an unconstrained problem. The alternative to this approach is to solve the constraint problem is applying the Lagrange equivalence. And what is the Lagrange equivalence? Is that, so Lagrange was a mathematician that has demonstrated that if x is minimizing this objective function with this set of constraints, then x will also be the minimum of this function here, with two different additions to it. The fact that we have to add a multiplier to each of the inequality constraints and of each of the equalities, constraints that are in the problem. So what does it mean? It means that Lagrange has in fact added one multiplier variable per each equality equations that are considered in the system. So now I'm increasing the number of variables that needs to be found by the optimization. Okay, so instead of having to find only the value of the x, so the decision, the state variables, I have also to find the value of the Lagrange multipliers. So I have more variables, okay? But what you can see here is that I have no more equality equations. So I'm back to a problem, which is a problem that tries to minimize an objective function without constraints, except constraints on the variables. Okay, so I have here a set of linear constraints that applies on the variables, but I have made this one and this one disappear from the list of constraints because they are included here in the objective function. But at the same time, and I should have added mu here, I have to find not only the value of x, but also the value of lambda. By doing this, I have in fact more decision variables because I have to add the Lagrangian multipliers plus the slack variables associated to the inequality constraints. I have also added the slack here, so it means that I have much more decision variables. But something which is interesting when I'm using this formula is that I can express the conditions of optimality of the minimum of the Lagrangian here by looking at where the gradient of the Lagrangian, setting to 0 the gradient of the Lagrangian. Okay, so now I have to find the value of lambda x and the slack and the mu in such a way that the gradient, which is the derivative of the Lagrangian with respect to x, with respect to the slack, with respect to the lambda and to the mu, that have to be equal to, or each one having to be equal to 0. Okay? And if I'm making the sum of how many variables I have nx plus ng plus nh plus ng. So those are the list of values that I need to calculate. And how many equations do I have? I have nx plus ng plus nh plus ng. So it means that I have a square system. Okay? And if I'm looking at what it means, now let's make the derivative of this equation. The derivative with respect to x is the derivative of the objective function. So it would mean find the value where the function is minimum. It has to be equal to 0. But adding to this contributions related to each of the equality constraints and to each of the inequality constraints. So this is the derivative with respect to x. But what is more important is that when I'm writing the derivative with respect to lambda, I'm obtaining here my set of equality equations. Okay? When I'm writing the derivative with respect to mu, I'm obtaining here the representation of the slack equation for the inequality constraints. Okay? And something which is also very important, I have the derivative with respect to the slack, and as it is a square, okay, it is the mu multiplied by the s. Yeah. Okay, so it means that now I have a system of a set of nonlinear equations, which is a square that I can solve as a set of nonlinear equations, for which I will calculate the value of x, s, lambda, and mu. Okay? There is only one that is difficult to solve here. This is this one. Because this one is equal to 0 if mu is equal to 0 or if s is equal to 0. And the difficulty is to choose between s and mu. Okay? And what does it mean? If s is equal to 0, it means that here s is equal to 0, it means that the inequality constraint is active. Okay? If s is not equal to 0, then mu has to be equal to 0. Okay? And if s is bigger than 0, then it means that this equation is going to be the inequality, meaning that the inequality is not at its bound. Okay? And in this case, I have to find the value, the mu has to be equal to 0, meaning that here there will be no contribution. Okay? And this is very important because indeed, if we look at the definition of the Lagrangian multiplier, being mu or lambda, what we can see is that the lambda is in fact, going back to here, this equation is equal to 0, okay? And needs to be equal to 0. So if now I'm looking at what is the definition of lambda, in fact, lambda is the variation of the function as a function of the variation of the equality constraints. So it means that if the equality constraint is pushing more, then the function is going to change. So the example is when we were talking about the transporting goods. So what will be the change in the cost if I'm buying a new truck to transport the good? This is the expression of the lambda, okay? And something which is important, so I have told you that in this equation here, when s is bigger than 0, mu has to be equal to 0. What does it mean? It means that mu is being equal to 0, it means that the objective function is not influenced by the value of the inequality constraints, meaning that the inequality constraint is not active. Okay? So it means that changing the value of the inequality is not going to change the value of the optimum function. Okay? So having this, then it allows me to solve the problem of the Lagrangian by solving this equation here, which will allow me to calculate what is the next value of x, knowing the value of x of the previous iteration. And now I'm going to say that the Lagrangian will be described by the first order, okay? Meaning that the square terms here will be eliminated, which means that if I want to be able to solve this, to calculate this matrix here, which is the linearization of the problem of the nonlinear problem, there will be a very difficult part, which is related to the calculation of the second derivative. Okay, the fact that as this function, which includes the derivative here, needs to be equal to 0, then I will have to calculate the second derivative of the objective function, but also of the second derivative of all my constraints. Okay? So it means that inside my system, as soon as I will have to solve an optimization problem, not only I will have to calculate the derivative of the objective function and the derivative of the constraints, because I need to solve a constraint even if I want to linearize them, but I will have to calculate the second derivative of not only the objective function, but also all the constraints, so that we will see, in fact, how we will see the slope or the curvature in the search space. Okay? And of course, the difficulty will be to calculate those values here. So the second derivative of each of all the functions, because it's the derivative of the derivative. Okay? And when we calculate the derivative, we have to make a perturbation. If we have to calculate the derivative of the derivative, we have to calculate the derivative on the, we have to make perturbations on the perturbations, meaning that we will have to make a lot of calculations to obtain the value of the derivative, with the risk of being in a, of still having in the nonlinear functions that we are going to solve, the fact that it might happen that we have derivative, that we have iterative processes inside. So it means that the calculation of the second derivative, if we do not have an explicit definition of the functions, will be quite complicated. Okay, so, but now, as I have this, then I will be able to solve, to make steps and iterations, so calculate the new value. And again, I will try to be smart by saying, okay, if the step defined by the first order of the gradient first order expansion of the gradient is not giving me the expected result, so it means that I'm not going towards lower value for the norm of the gradient of the Lagrangian, then I will have to do relaxation. Okay, so relaxation will always be there, and if the problem is quadratic, in fact, I will directly converge towards the solution. If not, then I will have to take actions to limit the steps that I'm doing to avoid going outside my significancy of the first order development. Okay, and this also gives me then back to a typical way of solving the problem of nonlinear programming problems is by assuming that the function, that the objective function is quadratic, which allows, in fact, to consider that I have a slope with a curve with a second order that allows me to formulate the problem by, on the one hand, linearizing the constraints, and on the other hand, making the assumption that the objective function has a curvature which is defined by a second order polynomial. And this allows me to define the directions where I have to search, and from there go to define what is the step lengths that I have to do in order to finally define what is the delta x that I have to realize. By doing this, I will be able to solve nonlinear problems. I will be able to solve nonlinear problems, iterative, meaning give a good initial point and you will find a solution. Give a bad point, you will not find a solution. Meaning also define in a right way the bounds, because the bounds is the difficult part. Okay, so the better you are in defining the bounds, the better system will be to solve the optimization. It remains one step to be solved, and this step to be solved is the integer dimension when I have nonlinear problems. Okay, so nonlinear problems are difficult to solve. We have seen a method, which was the branch and bound method, that was used in order to fix the value of integer variables to either 1 or to 0. Okay. And one could say that, okay, why not apply the same branch and bound approach by solving a succession of nonlinear programming problems? The problem of the succession of nonlinear programming problems means that each time we have to solve a new problem which is going to use an iterative process, which is not the case in linear programming, because in linear programming we have a linear system, we just have to invert a matrix. Here we have to make iterations, which makes the system a little bit more complex. Okay? And therefore, when we have to solve mixed integer nonlinear programming methods, what we can do is to use a trick, and the trick is the following, is that we can decompose the problem into steps. So one of the ideas, for example, would be to say, so let's start with a first initial guess of what are the value of the integer variables. In your case, select the technologies that are in the list. Okay, you pre-select which one are in the list. Now what you will do is that you fix the integer variables and then you solve the nonlinear programming problem. So you calculate what is the optimal pressure of operation of the heat pumps, for example, or the best heat exchange area of the heat recovery heat exchangers. Okay, for a fixed value of the pre-selected systems. When the system has been solved, then you say, okay, I have a reference. If there is an optimum, then I have an integer set. And what I'm going to do now is that I'm going to take all the values, so the operating pressure, the area of the heat exchangers, and I'm going to formulate a mixed integer linear programming problem with those values. Okay, that's exactly what you have done up to now. You have solved a mixed integer linear programming problem by assuming a certain efficiency for the heat pumps. Okay, so now, having assumed the efficiency of the heat pumps, then what you do is that you generate a new set of integer variables by solving a mixed integer linear programming problem. Much more efficient to solve than an NLP, a nonlinear program. Once you have done this, then what you will do is that you will say, okay, now I have a new set of integer variables. So I can go here, and I can restart here with a new NLP that will be solved with a new list of integer variables. Okay? Now, I want to be sure that I will not reproduce twice the same set of integer variables. So it means that I'm going to solve the mixed integer linear programming problem here by adding one constraint that is named the integer cut constraint that is going to tell with a set of equations, with one equation, which is an inequality equation in the linear domain, that you do not want to reproduce an integer set that you have already solved once here. Okay? I'm not interested in having a new one, in calculating a one that I have already seen. So what I'm going to say is that let's solve the problem with the mixed integer linear programming problem by adding this constraint, which is the integer cut constraint, that is going to tell me, give me the next best integer set. And I will be sure that the next solution will concern another set as the previous one. Okay? And with this new set, I will go back here and solve the nonlinear programming problem and then continue. And something which is important then is that there will be a certain time where this problem with the mixed integer linear programming constraints will stop finding solutions. We'll say, okay, I have no more integer sets to propose to you. And in this case, I will have converged and I will have solved the problem of the mixed integer nonlinear programming problem. So there is another constraint here, is that officially the linearization here has to satisfy some constraints. So it means that the objective function in the linear domain has to be compatible with the nonlinear function in the nonlinear domain. Okay? So those are constraints that needs to be added. They are added by the people who are programming those kind of methods, which allows you to solve the mixed integer nonlinear programming problem. But of course, you can see that you have to solve more than one nonlinear programming problem here. And you have to be sure that the system is going to converge, because if it tells you that it does not converge, it will discard the integer set that you have proposed. And if the system is telling you, okay, well, this one is not feasible, you have to be sure that it is not feasible because it is infeasible, and not because the nonlinear programming algorithm is not able to find the solution. Okay, so there is a risk that needs to be considered. Of course, those kind of problems are taking much more time because you have to solve a lot of NLP, and NLP means calculate the second derivatives, at least once, okay? So it takes time. And therefore, the better you are, again, in defining the initial integer sets, the better you will be in obtaining the solutions. Do you have questions about the nonlinear programming part? You do not have questions. That's because you have never applied the tools. So that's why Raphael is going to present the nonlinear programming problem that you will have to solve in this study. So Raphael is going to show you how we are going to apply the nonlinear programming, and how you will then at least have a certain feeling on how a nonlinear programming problem has to be stated and solved. Okay, the method that you will apply will be using the simultaneous approach with pre-different solvers that are available in Ample. Okay, so Raphael.